Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, I'm going to show you how to do the feed-forward calculation in a neural network with NumPy. If you don't want to code along, the relevant file is forwardprop.py in the GitHub repo. So we first want to import NumPy and matplotlib as usual. Okay, and let's create 500 samples per class. So what we're going to do is we're going to generate some Gaussian clouds. So we're going to have 3 Gaussian clouds. So the first Gaussian cloud is going to be centered at 0, -2. The second Gaussian cloud is going to be centered at +2, +2. And the third Gaussian cloud is going to be centered at -2, 2. Okay, and then we can create our labels. So that's just 0 times n class plus 1 times n class plus 2 times n class. And just so you guys know what it looks like, you'll be able to visualize this. I'm going to do a scatter plot. Okay, so that's for visualizing the data. And we're going to set d equals to 2. M is going to be the hidden layer size, so I'm going to set that to 3. And k is equal to 3, the number of classes. So now we're going to initialize the weights. So we know W1 has to be d by m. B1 has to be rand size m. W2 will be m by k. And B2 will be size k. Okay, so let's define the forward action of the neural network. It's going to take in X matrix, W1, B1, W2, and B2. And we'll use the sigmoid nonlinearity in the hidden layer. So that's 1 divided by 1 plus the exponent of minus x dot w1 minus b1. So z is the value at the hidden layer. Now we can calculate the softmax of the next layer. So that's z dot w2 plus b2. Remember, we exponentiate a, and then we set y to the exponent a divided by the row sum. So we did this in the last lecture. We return y. And now let's define a function to calculate the classification rate. So this is going to take in targets y, and it's going to take in the predictions p. So we have n correct. We'll initialize that to 0. And total, initialize that to 0 as well. For I and x range, length of y, and we just count up. So of course for every element we have to increase n total, and then only if the prediction is correct should we increase n correct. Okay, and then we return float of n correct divided by n total. Alright, so now we can actually call the forward function with our randomly initialized weights and calculate the classification rate. So p of y given x is equal to forward, you pass in x, w1, b1, w2, b2. And you get the predictions by doing the argmax on p of y given x on axis equals 1. Now we can assert that we've chosen the right axis to do the argmax on by doing this. So the length of the predictions should equal to the length of y. And then finally we can print the classification rate. Now, of course, this isn't going to be a good classification rate because we haven't trained the neural network yet, but this shows you how to do the forward direction in a neural network. So let's run this file. All right, so this is what the data looks like. It's 3 Gaussian clouds. And the classification rate is, as expected, exactly as expected, 1/3.
Okay, so in this lecture, we are going to implement process.py. Now, some people might be confused as to why there's a notebook in this video, but this illustrates an important point that I mentioned later in the FAQ, but I think some beginners maybe don't know about. So this is the idea that Python code works the same, whether it's in a Python file, so like a .py file, or in a notebook. So as you'll see, the code I'm going to use in this script, in this notebook, is the exact same as the Python script that you will see in this course. Okay, so Python code works the same everywhere. Okay, so by getting access to the Python file in the GitHub repo, you're actually getting access to the exact same code that's in this notebook. Okay, so I just want to make that clear. The code is exactly the same. It doesn't matter where you run it. You can run it wherever you like. Okay, so that being said, we're going to start by doing all the imports we need. So I'm going to import numpy as np, and we're going to import pandas as pd. You also see I'm importing an OS, but we don't need that part of the script in this video. Okay, so the next step is to import the getData function. So this part is a bit different between the notebook and the Python file. Since in the Python file, everything already comes in the folder, so you already have access to the data, since that also comes with the GitHub repo. But it's not in my Colab environment. So in my Colab environment, what I'm going to do is I'm going to go to my GitHub page, and I'm going to download this file. Okay. Oh, and so one mistake that some beginners make is they take this URL. Okay, so this is not the right URL. So this is actually an HTML page rendered as a table. Okay, so you don't want this HTML page. What you want is the actual CSV, which is this. Okay, so if you didn't see that, I clicked on the raw button to get to the actual CSV file. Okay, so we're going back to the notebook and we're going to download this file. Okay, so now we have the file. All right, so now we can implement our getData function. And remember, you don't need to do that locally because this file already comes with the GitHub repo. Okay, so we have our getData function. So inside the function, we call pd.readCSV to load in our data as a data frame. Okay. And if you want, you could do this outside the function too, and then you could call df.head to check out what's inside the data frame. In fact, let's just do that, just to see. Okay, so this is a little experiment, which is not part of the process.py file, but we're doing it in this notebook. So you can see what the data looks like after you've loaded it in. Okay, so here we have the isMobile column. So this is either 1 or 0 based on whether the device viewing the website was mobile. And we have end products viewed, which is the number of products that the customer viewed. We have the visit duration, which is the amount of time the user spent on the page. We have is returning visitor, which is either 0 or 1, based on whether it's a new visitor or not. We have time of day, which is a categorical input based on which quarter of the day the user visited the website. And then we have the user action, which is our target, which is encoded as an integer from 0 up to k-1, where k is the number of classes. Okay. And in fact, we can check the number of classes and their distribution by doing this. So time of day, and then we can call hist. So this draws a histogram of the different labels. So we have 4 labels, 0, 1, 2, and 3, and this is their distribution. So we have a little bit more of these, a little bit less of these, a little bit less of these, and a little bit less of these. Okay, so now that we know that that works, we can work to process this data. Okay. So the first thing is that it's much easier to work with NumPy arrays. Okay, so we have data equals df.to NumPy. Now, just a short note about this function. So this function clearly converts the data frame into a NumPy array. But in the past, this is one of those functions that has changed very frequently as the years have gone by. So in older code, you might see something like df.asMatrix, or you might see df.values. So these all did the same thing. Now, one thing to not get confused about is one thing I saw recently, where a student found out that df.asMatrix did not work, and what they tried to replace it with was this other function, which looks the same but is not the same. So it was np.asMatrix. Okay, and that takes in a data frame or any other kind of data that can be converted into a matrix. Okay, and the reason these are not the same is because asMatrix does not return an actual matrix object. It returns a NumPy array, versus numpy.asMatrix returns an actual matrix. Okay, so you have to be aware of that. And this is stuff you would have learned in the previous prerequisite free NumPy course. Okay, so if you haven't taken that, please do, because it has a lot of important information about these little coding things that you really need to know if you want to implement data science scripts. Okay, and the reason I mention this is because this guy, he was on the Q&A and he used this, and then he got very angry because he thought, oh, nothing's working. And, you know, he didn't realize it was his own fault because he didn't know that these were not the same. So he thought he could replace this with this. And then, you know, he really just frustrated himself. Okay, so don't do that. If you have a question on the Q&A, just ask the question. Don't go down your own path and then, you know, confuse yourself. So the point of this is, it's not to point out that someone made a mistake or anything like that. The point is that part of being a good data scientist programmer, or a data scientist, I guess, who does programming, is to understand the whole ecosystem, right? It's not just to copy the code that the instructor wrote, because, you know, maybe 1 year or 2 years from now, the code that the instructor wrote is not going to be the same. So it's this adaptability that you need. And it's a higher level, more broad understanding that these things can change, and also getting used to them. So getting used to that process, understanding that process, that these functions will change over time, that one or some other library is going to change over time on you. And either you have to update your code or make sure you're installing the right versions of the libraries that you need. Okay, so that's the point, is to not get stuck, because if you just get stuck every time something changes, well, you're going to be stuck a lot. right? So you want to be able to adapt to these things. And that's what makes a good programmer versus a bad programmer. And, I would like for all the students in this course to become good programmers, okay? So this gives us a NumPy array, which is not the same as a matrix, okay? And then we would like to shuffle our data. So shuffle our data, p.random shuffle. And this function is a little weird because it doesn't return anything. It just shuffles the thing in place that you pass in. Okay, and this shuffles by the row. So don't worry about shuffling everything. Like the columns won't get shuffled, just the rows. Okay. And so the next thing we're going to do is we're going to split up the features and the labels, so the inputs and the targets. Okay, so split features and labels. So we'll call the inputs X as usual, and we'll select all the rows in all the columns up to the second last. And for the targets, we will select the last column. Okay, and we'll also convert this to an int. Okay, now as you recall, our time of day dimension is categorical. So it's encoded as 0, 1, 2, and 3, I believe. And so what we would like to do is, since categorical data encoded as an integer isn't appropriate as input for a machine learning model, well, not all machine learning models at least, including this one, we would like to one-hot encode this categorical data. Okay, and this should be np.n32. Thanks Colab for the syntax highlighting. Okay, so yeah, we would like to one-hot encode our X data. So we'll begin by getting the shape of X, and you'll see why we need that shortly. Okay, so now we're going to create a new array called X2. So this is going to be the final data matrix, okay? We'll just initialize it as an array of zeros and of d plus 3, okay? And so some people have asked, why is it d plus 3? And this is because we have 4 categories, and if we want to one-hot encode that, we'd have 4 new columns. But we can also replace the existing column, which is why we only need to add 3 more, okay? And so the first thing we'll do is we'll just copy all the non-categorical data first. And so luckily, it's just the first d minus 1 columns. Okay, so we go all rows, columns up to d minus 1 equals, so now we're taking from the original X matrix, all rows up to d minus 1. Okay, so these are the non-categorical columns. Okay, and so for the actual one-hot encoding, so that's the rest of the columns, there are 2 ways to do this. And for the sake of this course, I'm just going to do it the sort of intuitive, easier way, but it's not the most efficient. So we're going to loop through each sample one at a time, and we're just going to one-hot encode each sample as we loop through it. Okay, so we'll first get the actual encoded value that's encoded as an integer. So this would be at row n, column d minus 1. Okay, and then what we would like to do is assign that into the appropriate place in X2. So it's still row n, it's the same sample, but its column is t plus d minus 1. Okay, and we set that to 1. All right, so why is it t plus d minus 1? So d minus 1 would give us the final column in the original matrix, which is, I guess, the 4th last column in our new matrix, and then we're just adding t to that. Okay, so it's either going to be d plus 1 or d minus 1 plus 0, d minus 1 plus 1, d minus 1 plus 2, or d minus 1 plus 3. Okay, one of those should be set to 1 based on what t is. Okay, so hopefully you understand how one-hot encoding works. And just for completion's sake, I'll explain the second method as well, but I'll leave it in a comment. Method 2. So this is where we say z is equal to np.zeros and 4. So this is just the one-hot encoded part. we're just going to do it separately. And so we do z equals np.arange of n. So this is going to select each of the rows one by one. And then we have corresponding columns to select, okay? So it's d minus 1 as type np.in32. And then we set those to 1. Okay, so how does that work? So basically, what we're doing is we're passing in a set of tuples into the rows and columns. So it's basically row 1, row 2, row 3, and so forth. And then the corresponding column 1, column 2, column 3, and so forth. And we can set that to any value we like. Okay, so that's the syntax we use above. Okay, and then in order to assign this to x2, we would simply do x2, all rows, the last 4 columns, and then we just set that to z. Okay, so it's not simple, but it's more efficient. Okay, so the next step is to just assign x2 back to x. Assign x2 back to x. I'm not sure why I did that originally. I guess the x variable is slightly easier to work with than x2. Okay, and the next step is to do a train test split. Okay, so we have x train is equal to x up to the last 100 points. Okay, so all of the points except the last 100 will be for the train set. And then we have y train is equal to y, and then the same indexing. And then we have x test, which is equal to x, and then we have the last 100 up to the end. And we have y test equal to y minus 100 up to the end. Okay? And so the next pre-processing step we're going to do, since all the other columns are numerical, we're just going to use a simple method of pre-processing, which is to standardize the columns. Sometimes we call this normalize, but I think standardize is more specific. Because normalize can mean multiple things. Okay, so we want to normalize the other columns. Oh, actually, not all of the other columns, just columns 1 and 2. So normalize columns 1 and 2. So for I in 1, 2, okay, we're going to compute the mean from the train set. So this is all rows, column I, mean. Then all rows, column I, standard deviation. Okay, and so this is how we do standardization, to give the column 0 mean and unit variance, unit standard deviation. Okay, so we're changing the same column, all rows, I equal to x train. So we're doing all rows at once for this particular column. We subtract the mean, divide by standard deviation. Okay, and then we do the same thing for x test. Okay, and so once we've done that, we are done our pre-processing. So we can return x train, y train, x test, and y test. Okay, so let's run this. And let's just see that it works. It's always nice to test. Okay, so everything seems to be working well. You can also check the shapes and everything, just to see we get back what is expected. Okay, so we have 400 points in the train set, 500 points in the test set, and there are 8 input features. Okay. Now, since for some models we're only going to study binary classification, we also have a function to convert the data into binary format. So basically what we're going to do is ignore the other 2 classes. Okay, so we have get binary data, and we have this up here to get the data, and we're just going to filter out all the classes that are not 0 and not 1. Or in other words, we're going to keep class 0 and class 1. Okay, so we have x2 train is equal to x train, and we're going to select yTrain less than or equal to 1. Okay, so some people may find this syntax confusing, so let's explain what this does. Okay, so it's good to go in order of operations. So in this case, inside to outside. Okay, so what does this do? This compares yTrain, which is an n-length 1D array, to some number, 1. Okay, it's less than or equal. So what would that do? That would return a Boolean array. So we can even do it out here just to test it. Right? So we have less than or equal to 1. So this returns a Boolean array. Okay, true or false. Okay, so basically this works as an index into xtrain. So it's going to keep the values where we have true, or where the corresponding index says true, and we're going to throw away the ones where it says false. Okay, and so that when we do the same thing for y2 train equals ytrain, where ytrain is less than or equal to 1. And then we're going to do the test set. And you see that we're doing this based on the target value. Okay, so we're selecting samples which have target that are 0 or 1. Okay, so x test, y test less than or equal to 1, y2 test equal to y test, where y test is less than or equal to 1. Okay, and then we return x2 train, y2 train, x2 test, and y2 test. Okay, and let's just test this out. I'm going to say this is equal to get binary data. Okay, so that works. And now let's check the shape. Okay, shape, shape, shape. Okay, so we have 323 samples in the train set, 75 samples in the test set, and we have 8 input features. Okay, so that's process.py. Check it out on GitHub. Or better yet, type it yourself. Okay, so in this lecture, we're going to continue on with our e-commerce project. And in this lecture, we're going to practice what we learned in this section, basically. Okay, so that's how to make predictions with an ANN. Okay, so just to keep in mind, we don't yet know how to train, but we do know how to use the model to make predictions. And so what's going to happen is we're just going to get random predictions. And in the later sections, we'll learn how to make those predictions actually good. Okay, so let's begin by doing our imports. So we'll import numpy as np. And so you won't see this in the Python file for this course because it's going to be a bit different how we import things. So because this is a Colab notebook, we don't have the Python files directly. We could download them, but that's going to get kind of messy, so we're not going to do that. So if we had the process.py file locally in the same directory, so this would work whether you're doing local Python or Python on Colab or in a Jupyter notebook, you could just do this. So you could do from process import get data. Okay, so that would be assuming you have the previous process.py file in the same directory. Then you could do this. Since we don't, because this is Colab in the cloud, we're just going to repeat what we had there. So import pandas as pd, and then we're going to take process.py. Okay. And don't forget to download the dataset if you're doing this on Colab. Okay, so here we download the dataset. And here is the code for process.py. Okay, we basically just need get data. Okay. So we have this. Okay, so now we're ready to load in the data. So since this is only making predictions, we're only going to bother using the train set. So we'll say x, y, and ignore the test set. We'll say get data. Okay, so this gets the data. And then we're going to create randomly initialized weights. Okay, so we'll set our number of hidden units to 5. So we'll set m equal to 5. We'll get the dimensionality of the input. So remember, x is of shape n by d. So d is in the second dimension. That's the number of input features. So at index 1. Then we'll get the number of classes. So this is the number of outputs of our neural network. Okay, so we'll say k is equal to the length of a set of y. So how does that work? So recall that y is only going to contain integer encodings of the targets. So when we convert that to a set can only contain unique items. Okay, so when we get the length of that set, that's effectively getting the number of unique categories. Okay, so then we'll create our weights. So we'll say W1, so this is the input to hidden weight, is a random normal with input dimensionality D and output dimensionality M. Okay, so that goes to the hidden layers. And we'll say B1 is going to be initialized as zeros. You could also initialize this randomly, but we won't. Okay, and then we'll have the hidden to output weights. So that's W2, call it mp.random.randn. Now it's M going to K, okay? And then B2 is again zeros of size K. Okay, so that's all our weights. So the next step is to create our functions to actually compute the output. Okay, so we'll begin with softmax. So we have the softmax that takes in the activations. And we'll first exponentiate A. So we'll say expa to np.exp, passing in A. And then we'll take that and we'll divide by its row sum. Okay, so we say return expa divided by expa.sum, and then we pass in axis equals 1 to make sure we don't sum the whole thing, but only across the rows. Okay, and we also say keep dims equal to true, and this ensures that broadcasting will still work. So if we don't do this, then it's going to fail. We'll get an error. Okay, so our softmax function is done. And now we have our forward function, which does the matrix multiplies. Okay, so it's forward, takes in our input data x and all of the weights. Okay, so it's W1, B1, W2, B2. And you can imagine if you had more layers, you might want to refactor that. Okay, so we'll get the hidden layer first, the hidden output, and we'll assume we're using the tanh activation. So we'll say np.tanh, and we'll pass in the input data x. We dot it with W1, and we add B1. Okay, so now just to recap, why do we say x.w1 instead of w1 transpose x like we do in the theory lectures? So just to remind you guys of why it's this way, this is because in the theory lectures, when we're discussing math, we're usually only discussing a single sample of x. And so that's a d-dimensional vector. So when you want to multiply d by m matrix by a d-dimensional vector, you have to transpose w first and then multiply by x, okay? Assuming that we use the convention that vectors are column vectors, so it'd really be d by 1, okay? So in theory, we'd be doing m by d times d by 1, okay? And that works because the inner dimensions match. But for this, x is of shape n by d, right? We have multiple samples at once, which is not usually what we talk about when we talk about the math. Okay, so in this case, we take n by d times d by m. And so that combines to give us an n by m. Okay, so that's why x comes before w1. Okay, and then we'll do the second step, the second layer, which is the softmax of z dot. So we're just doing this all in one step, right? This is really the A, the activation. So it's z.w2 plus b2. Okay. And so now we can use our functions to get the output. Okay, so we have p of y given x equals forward, and then we pass in all our stuff. Okay, so we have x, w1, b1, w2, b2. Okay, so let's run this. It's always a good idea to check the shapes so we understand what we're working with. Okay, so let's print out the shape. Remember, we want this to be n by k. So is this n by k? And I believe it is because we have 400 samples and 4 classes. Okay, so that makes sense. And now we are going, so just remember that these are not the predictions yet. These are the probabilities. Okay, so for example, this is the probability that the first sample belongs to class 2. And this is the probability that the first sample belongs to class 1. And so on and so forth. Okay, so how do we get the predictions? We take the argmax. So we take the argmax along the columns. So for each column, we take the max in. So for example, out of these numbers, so these would be all the predictions for the 4 classes, and this is the max. So in this case, the prediction would be class technically 1 if we're talking about math, but since this is programming, these categories are encoded as 0, 1, 2, and 3. So in this case, it would be class 0. Okay, so we'll say predictions is equal to the np.argmax of p of y given x. And we have to say it's along the column, so we say x is equal to 1. Okay, so that's our predictions. And let's just check the predictions as well. See what we got. Okay, so as you can see, so our guess was correct that this would be predicted as class 0. And just remember that these are all random, right? So these are not actual learned predictions. Okay, but this is the shape we expect. It's a one-dimensional array containing class predictions. Okay, so now just for completion's sake, let's check out our accuracy. So how good we did, how good our model does, even though we don't expect it to do that well. Okay, so we'll say def classification rate. It's going to take in the targets and the predictions, and it returns the mean of y equals p. Okay. Now, just in case you're wondering how this works. So basically, you have to work from the inside out, okay, in the order of operations. So first consider this, okay, y equals p. We know that equals does a Boolean comparison. So return true if the elements are the same and false otherwise. Okay, and it does this in an element-wise fashion because NumPy is smart and it knows how to do that with NumPy arrays. Okay, so if we check this, right, so this should be, that's only the name of it inside the function, but outside the function it's predictions. Okay, so it's an array of trues and falses. It's true when the prediction matches the target and false otherwise. Okay. Now, your next question might be, well, how can we take the mean of an array of trues and falses? And how that works is because in Python, true is treated like 1 and false is treated like 0. Okay, so how would you compute the classification rate if you had an array of 1s and 0s? Well, you would add up all the 1s and then divide by the total number. Okay, so that's conceptually what you would do. Add up all the 1s, divide by the total number. That would be the number you got correct divided by the total number, which is the classification rate. But what we're doing is the mean. So why does that work? Well, my claim is that adding up all the 1s is the same as adding up the whole thing. And of course that makes sense because we only have 0s and 1s because we only have trues and falses. Trues are 1s and falses are 0s. So if we add up everything, we still get the sum of all the 1s. Okay? So now what is adding up everything dividing by the total number? Well, that's just the sample mean, which can be computed by calling np.mean. Okay, so that's why that works. Okay, so we have the classification rate, and now we're just going to use it. Okay, so we'll say print score, say classification rate. No autocomplete. Oh, thanks, Colab. Okay, and we'll pass in the predictions. Let's see what we got. Okay, so we got 31.5% accuracy. Of course, again, we don't expect that to be good because we have not yet trained this model.
Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python. In this lecture, we are going to do a few mini quizzes. I've been told by some students that they don't like their video to be interrupted, and so these quizzes are provided in video format rather than static checkboxes, which would interrupt your video. However, I don't want you to take the easy way out and just watch this video straight through. I actually want you to put in effort and answer these questions. The first question is as follows. Suppose we removed all the nonlinearities from the neural network. What is the result? You're given three choices to choose from. Number one is you get a neural network for regression since the output can now take on any value. Number two is you get linear regression. And number three is it doesn't change anything. This is still a neural network that can be used for nonlinear problems. I'll give you a second to think about this, or you can pause the video and come back when you think you've got the answer. The answer is you get linear regression. Notice how if you remove the nonlinearities, you can simplify the equation by multiplying out the weights and biases and grouping them together. And this is the exact same form as linear regression. This is because multiplying two matrices together just gives you another matrix. Next question is a calculation question. We have an input x equals 1, 2. This is a 2B matrix of size 1 by 2. That means there's one sample in 2 dimensions. The input to hidden weights are 1, 1, 1, 0. That's a 2 by 2 matrix. And the hidden to output weights are 0, 1, 1, 1. That's also a 2 by 2 matrix. Assume the hidden layer nonlinearity is the hyperbolic tangent and that the softmax is done at the final layer. There are no bias terms. Here are the possible solutions. Your job is to choose the right one. I'll give you a minute to think about it, or you can pause the video and come back when you're done. Let's first go through the incorrect answers before we get to the correct answer. 0.76 and 1.76 can't be correct because the sum is not 1. Also, the output should be two-dimensional. The first dimension should be 1, meaning we have one sample, and the second dimension should be 2, meaning we have two classes. 0.27 and 0.73 also can't be correct for this same reason. This is only a one-dimensional array. 0.54, 0.46 has the right shape and the rows sum to 1, but these are the wrong values. We won't be doing a full calculation in this video since we already did a full example earlier in this section. This leaves 0.27, 0.73, which is the correct answer. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. Since this was a pretty long section, let's summarize everything we did. Remember that this course was designed to develop concepts based on binary linear classification, specifically using logistic regression. We saw that a neural network is actually just a bunch of logistic regression units combined together in a specific way, in particular in layers. We saw that instead of being limited to two output classes, we can have any number of output classes by using the softmax instead of the sigmoid. We learned about the alternatives to using the sigmoid in the hidden layers, such as the tanh and rel-u activation functions. We then looked at how to write the softmax in code. Next, we wrote a full neural network in code, incorporating what we know about coding the softmax function. Most importantly, we saw the data we wanted to classify, 3 blobs in two-dimensional space. It's important to be able to visualize what you're doing. Finally, we applied our neural network code to make predictions on our e-commerce dataset, along with some useful pre-processing steps. The main goal of this section was to answer the question, how do we go from input to output in a neural network, and what do those outputs mean? One key point in this section is that all the weights in our neural network were random. Because the weights are just random, the prediction is also random, and so of course they aren't accurate. In the next section, we are going to learn how to change those weights so that our predictions can be accurate.
So in this short lecture, I want to tell you about my suggestion box. The idea behind this is analogous to the kind of suggestion box you would find at a restaurant. You can write down your thoughts and leave them for the owner to look at to give them feedback so that they can improve your dining experience. In order to share your thoughts with me in my suggestion box, please go to lazyprogrammer.me/suggestions. Here you will find a simple form where you can tell me anything you like. I have a few suggested fields, but none of them are required. However, they would be helpful for me to know. For example, tell me your background. I think someone coming from a background in marketing is going to have very different feedback compared to someone coming from a PhD in physics. Tell me what course you are taking so I have some idea of what you are talking about. Obviously, the more specific you are, the better I can help you. Tell me how difficult you thought the course was. Was it too easy? Was it too hard? Tell me if there was something I neglected to explain. For example, was there some word that I used that you have never heard of? Was there Python code that you haven't seen before? Tell me what you thought was missing from the course, even if it was just something small, like you missed explaining this line of code. Were you looking for an algorithm that wasn't included? This is helpful for me, but it's also helpful for you because many times students are looking for an algorithm or an explanation in the wrong course. So I can say, actually, I teach that algorithm or I explain that thing in such and such course, and this isn't the right course, so have a look over there. Are there any topics you want to request that were not included in this course? For example, maybe you signed up for a deep learning course and you were looking for CNNs, but the course didn't have CNNs in it. Let me know. Finally, let me know your suggestions for future courses. If there's a particular topic you want me to teach that I don't yet have a course about, such as gradient boosting or transformers or even quantum mechanics, let me know. Finally, there is a big text box for any comment you want to write. You can write anything in this box and make it as long as you want. In fact, the longer the better. If you think I talk too slow or I talk too fast, let me know. If you think my prerequisite instructions aren't fair, let me know. I want you to be as specific and as detailed as possible. A lot of the time people give me comments that I can't really act on, which is unfortunate. And this is often because they are too generic and not specific enough. Tell me exactly what lecture and exactly what timestamp you're referring to. If you want to refer to a question on the Q&A, include a link. Be very specific and give me concrete examples so that I know exactly how to act on the information you've given me. Thanks for listening, and I'll see you in the next lecture.